Today we're going to talk about the theory of plate tectonics. And plate tectonics is one of the most important theories in geology and earth science. And it says that the Earth's crust is made of giant moving plates. Now that's a pretty simple statement for being one of the most important theories in geology and earth science. And like any good scientific theory, it needs to explain patterns and observations that we see about the world. So plate tectonics helps to explain the location of land masses in the present, past, and future. It also helps explain the physical features that we see, like mountains, right? Mountains, volcanoes, and islands. And it also describes earthquake, okay? But first we took a pretty basic idea and made it more complicated. So let's break that back down. Let's talk about the crust. So if I was going to have my favorite deep dish cherry pie dessert, I'm going to expect for the crust to be on the outside. So I'm going to order a pizza with my study mates from our science class. It's going to be a pepperoni pizza. I'm going to expect for the crust to be on the outside. Now the same thing is true for planet Earth. So if I take a look at this diagram that I've just quickly drawn of the Earth, this shows me the four main layers of the Earth. And just like with my pizza and my pie, I'm going to expect to find the crust on the outside. Now for the Earth, the crust is the thinnest layer, and it's made of solid rock, which would not make for a very good pizza or pie. The next layer is going to be the mantle, okay, and it's made of molten rock or magma, and it's actually a plastic solid. So a plastic solid is something like silly putty or maybe raw dough. It's able to change shape, it flows and moves, but it's not quite as loose as a liquid. It's not going to spill all over the place like if you accidentally knock over a glass of water. Now our next layer is going to be the outer core, which is the only liquid layer, the only truly liquid layer in the Earth, and it's actually liquid metal. It's mostly nickel and iron. And of course, if you're going to have an outer core, you need to have an inner core. And it's solid metal, also mostly nickel and iron. So now we understand what we're talking about when we say the Earth's crust. But where are these tectonic plates actually coming from? Well, if you've been to a party and you've had a delicious bowl of nacho cheese, then you know that if you have the nacho cheese when it's still warm and freshly melted, nice and hot, then it's going to be pretty liquidy, pretty easy to get on your chip. But the longer that nacho cheese sits out and starts to cool, then it's going to cool and it's going to contract, or the molecules in the cheese itself are actually going to get closer together. And when that happens, you start to see cracks forming on the surface of the cheese, right? And the longer you let that go for, the longer you leave out this bowl of nacho cheese, the more of those cracks are going to show up, the bigger those cracks are going to get, and the deeper they're going to go until finally two cracks connect, right? And they make what is basically pretty crusty cheese, just like the crust of the Earth. And so if this bowl of nacho cheese was the Earth, then this actually becomes this crusty piece here that's cooled off, actually becomes like a cheese plate, like a cheese tectonic plate, right? And so on the surface of the Earth, the crust of the Earth, a very similar thing is happening. So the mantle that's made out of molten rock It's going to be hottest towards the center of the Earth, and it's going to cool off as it gets closer to the crust, okay? So there's these things always bubbling up through the mantle, and they're called convection currents. And that just means that heat is moving from the center of the Earth out towards the crust, and as it does that, it's going to go up, out, hotter and hotter as it's hotter as you move in. It's going to push the hot material up, hot, and then finally it's going to start to cool and actually fall back down. So you kind of get this sort of lazy J shapes that make the convection currents going up through the mantle. Now, as it does that, it's pushing hot magma up towards the surface, just like if you had freshly melted nacho cheese. It's going to be nice and warm still in the center of your cheese, right? If you dug down there with your chip, okay, before the cracks get too bad, you can still get some good cheese. And the same would happen here with the mantle. It'd be nice and pretty liquidy down there. But what actually happens is when it gets pushed all the way to the crust, then it's going to come out here all the way to the crust, and it's going to start to cool. And when it cools, it's going to form rock. And when it does that for millions of years, which it's had plenty of time to do on planet Earth, our tectonic plates started to form hundreds of millions of years ago. It's going to come out here, it's going to cool off, and it's actually going to form a plate. And I'm doing these plates in blue because lots of people forget that the ocean floor is also a tectonic plate, so it's not just the dry land masses. So that, again, those convection currents are pushing up the hot magma towards the surface, they're cooling, and they're going to form nice plates along the surface of the Earth. Now at this point, the entire surface of the Earth is covered in tectonic plates, but to keep this diagram kind of visible, I'm not going to color the whole thing in here. But what you have, because there's convection currents everywhere in the mantle, right, not just on one side, you have those convection currents pushing material up and out. What actually winds up happening is that once the plates are formed, because the convection currents are always bubbling, the convection currents are going to push the plates in different directions. So these two plates here are actually going to move apart from each other because convection currents in the mantle are bubbling up, pushing hot material up and out, and then it starts to cool on the surface and fall back down. So that's why we see land masses at the different places on the globe where we do. And of course, if you have convection currents on one side of the planet pushing things around, you also have convection currents here on the other side pushing things around. Now, if you take a look down here at this diagram, this shows the modern day tectonic plates. Let's pick a different color. This shows the modern day tectonic plates. Okay? Just on the flat world map like you would normally see in geography or earth science class. And if you take a look here along the red that I'm drawing, you can see that this is the continent of South America, right there below North America where we would expect to see it. But this whole purple portion is actually the tectonic plate that South America sits on. So tectonic plates are larger than the continents that are a part of them. And it's also important to notice that this area down here, while it might look like an ocean from a normal world map, is actually an oceanic tectonic plate because tectonic plates cover the entire surface of the Earth. The crust is made out of them, right? And so that whole green portion down there is going to be a large oceanic tectonic plate as well. And finally, while these are the modern day plates over here, we can take a look at some historic plates, some ancient plates, okay, and how the continents used to be arranged and the plates used to be arranged then. We can see here that this particular creature, fossils of this animal have been found on both South America and Africa because they used to be connected to each other. So this brown swath here shows where those fossils are found. Now, this plant over here in the corner is also found across Australia, Antarctica, India, Africa, and South America. And all of these continents or subcontinents sit on different tectonic plates that used to be positioned next to each other. And plate tectonics, again, because of the convection currents welling up through the mantle, coming up, cooling off, and forming that crust on the top, okay? The tectonic plates describe why we have the land masses where they are today.